Imagine riding in a self-driving car toward a busy city intersection. Suddenly, a massive delivery truck pulls up directly into the lane next to you. Your car might be packed with state-of-the-art cameras and laser sensors, but it's running into a hard physical wall. It cannot see through solid objects any better than you can. That wall of steel is currently blocking the most important piece of information on the road, the traffic light at the intersection. The car is now in a blind spot. It cannot safely roll into that intersection without knowing if that hidden light has already turned yellow or red. Relying entirely on this physical line of sight turns a routine blocked view into a dangerous gamble for the car software. To solve this, engineers use a technology called vehicle-to-everything communication, or V2X. Think of V2X as an extended sensor. Instead of just looking at the road with a camera, the car uses a wireless antenna to digitally listen to the intersection itself. The traffic light broadcasts its status as a radio signal. This signal passes right through the solid truck and reaches the car's antenna. This incoming data stream feeds directly into the internal brain, where it merges with information coming from cameras and lasers. This gives the vehicle a digital perspective that reaches around corners, allowing it to prepare for traffic conditions long before they are physically visible. While this removes the physical blind spot, relying on an invisible digital network creates a new, unseen vulnerability. The flaw with any wireless network is that data can get stuck. Signal interference or a crowded network can cause information to arrive late. Engineers track this using the age of information, which measures the total time from message creation to actual processing. Even if data travels quickly, if it sits in a queue for a second, its age becomes too high to be useful. For example, the traffic light might generate a message saying the light is green, but because of network congestion, that message takes 2 full seconds to reach your car. In those 2 seconds, the physical light on the street has already switched to red. If the car acts on that old news, its internal map of the world is no longer in sync with the physical reality of the road. To prevent a crash, the car's brain must constantly check the age of every packet. If the data isn't fresh enough, the system is programmed to ignore it entirely. In autonomous driving, receiving a perfectly accurate message that is 3 seconds old is just as dangerous as receiving no message at all. Let's return to our intersection. The delivery truck shifts forward, and for a split second, the car's camera gets a direct view of the physical traffic light. It's glowing red. Now the car faces a direct logical conflict. The wireless network is sending fresh data saying the light is green, but the physical camera is looking at a red light. This could happen because of a local transmission error, a misconfigured light, or even someone sending false data into the network. When the digital sensor and the physical eyes disagree, the machine has to decide which reality to believe. If the car were to prioritize an external signal over the physical evidence directly in front of it, the system would eventually make a choice that contradicts the real world. The solution is a process called cross-verification. This is a continuous logic loop where the car's brain aggressively pits the network data against its own cameras and LiDAR sensors to find any inconsistencies. If there is a mismatch, or if the digital data arrives too late, the car immediately stops trusting the network. This triggers a safety limiting mode, allowing the car to keep driving, but with much stricter rules. The car severs its connection to the unreliable data, slows down, and relies exclusively on its local cameras and sensors to bring the vehicle to a safe, controlled stop. Ultimately, true safety in autonomous driving comes from the programmed wisdom